We are taking the unusual step of starting at chapter 20 in this semester. It's nice for us to spend a chapter studying organic chemistry briefly. It fits in pretty nicely with sort of what we end with in Gen Chem 1, with drawing the structures and the bonds and stuff like that. So this is just a chapter about how organic compounds form, and we will classify and name them. But we put it at the beginning of the semester because we're going to refer to these types of compounds throughout the whole course. So it's nice to be able to draw their structures and know their names to it. Yeah.
Will we be going back to, I think we ended on like 11?
We ended on 11, so
12
yep. So we'll start on 20 right now, and then we're going to go back to 12 and go in order from there, 12 through 19.
Okay.
So
You're not going to cover 11?
No, we do cover 11, yeah. We ended with 10 last semester, yeah, okay. We ended with 10 last semester, so we're going to go back to 11 after this, 11 through 19. Okay, cool, thank you. So let's start out with chapter 20, Organic Chemistry. It's the study of carbon-containing compounds. And that word organic has gotten hijacked by various different sources over the years. In chemistry, it's very straightforward. Is it carbon-containing or not, pretty much? And that's an organic compound. The chemical organic term really has nothing to do with how it was farmed or what type of pesticides were used or anything like that. So it also has nothing to do with natural versus synthetic. Right? There are natural organic compounds. Pretty much everything that it's made out of proteins and carbohydrates is a natural organic compound, and there are synthetic organic compounds that are created in the laboratory. So gotta get that out of the way first, just to make sure that we're good with that definition. So that's here. Let me plug in here so I don't drain out on it while we're going here. But carbon is really unique. We'll talk about that. Plug in right here. There we go. So the reason we have organic compounds being an entire class of compounds and an entire chapter in this course, and if you go on to take more chemistry courses, you'll take a whole year of organic chemistry. The reason carbon is so interesting is because of its bonding pattern. Okay? In order for carbon to have no formal charge, and given that it starts with 4 valence electrons, how many bonds will carbon make? What do you think? Carbon will make 4 covalent bonds, right? And no nonmetal really will make more than that. Okay? In terms of covalent bonds, silicon can also make covalent bonds, but they're not nearly as strong as carbon's bonds. And other nonmetals make fewer covalent bonds, 3, 2, 1. Right? So carbon is unique in that it makes 4 very strong covalent bonds, which gives us almost an infinite number of different compounds that can be formed, right? Carbon can make chains, it can make rings, it can bond with other atoms. So there's just a tremendous diversity in the ways that carbon can bond. So let's look at the main bonding patterns that carbon has. Tetrahedral is when something has 4 bonds to it like that, and I'm going to draw one wedge coming out towards you and one dashed line going back away from you, something like that. Okay. And when you do that, here, maybe it would be even a little better if I drew this wedge one off to the side just a little more. But we draw a really nice tetrahedral carbon like that, so that no 2 bonds are straight across from each other. And in a true tetrahedron, no 2 things are straight across from each other. In fact, they are all 109.5 degrees. Okay, that's the ideal bond angle of a tetrahedral atom, like that. So, tetrahedron, right, that's sort of the standard way of drawing it. You can do that in any direction, right? For instance, if I put the 2 bonds in the paper right there, then the wedge bond and the dash bond would be like that. Okay? But to get the perspective correct, the wedge bond and the dash bond have to be next to each other. Okay? We will never actually see the wedge bond and the dash bond across from each other, okay, on that, just due to the way the perspective works. Okay? So either, and those are pretty much the same thing, just sort of rotated. Okay? When we are not being careful about the shape, we'll draw it like this. Right? But when we see a carbon drawn like that, up, down, left, right, we just have to know that that's a structure that's just merely showing what atoms are attached to that carbon, not necessarily the correct actual bond angles. Okay? So let's just write not actual bond angles. Okay. Okay. So, tetrahedral carbon that makes 4 single bonds, 109.5 degrees apart from each other. Okay. Trigonal planar carbon would be one that is a carbon that's attached to 3 atoms. So how do you attach carbon to 3 atoms when it has to still have 4 bonds?
2 single bonds, 1 double.
2 single bonds, 1 double bond. So carbon, 2 single bonds, 1 double bond. Okay. That ideal bond angle, what would that be?
120?
Yeah, if you're taking a circle and dividing it into 3 equal parts like that, the ideal angle of that would be 120. Okay. And then there are 2 ways to have a linear carbon. That would be when the carbon is just attached to 2 atoms. So what's one way? Two double bonds, right? 2 double bonds. Okay. So something like that. If we do 2 double bonds to carbon, that ideal bond angle would be 180 degrees apart. Okay. But what's the other way to get 180 degrees?
A single bond and a triple.
Single and a triple. That. Okay. So, those 3 shapes are about the only shapes that a carbon can take on. And these 4 bonding patterns are really the only bonding patterns that we will see for a carbon that has no formal charge. Okay? That means each bond that it forms brings in 1 electron to get up to the octet. Right? So we'll get used to seeing carbon like this. Sort of as we mentioned before, carbon is pretty much the only element that can form stable chains, especially. Okay? So big, long structures of connected carbons. Okay? And that's because the CC bond is very strong. So we need at least 2 bonds to form a chain, and those remaining bonds can be used to form things connected to the chains. Okay? They're usually hydrogens, but we can connect other carbons, and we can connect other atoms too. So we're going to start, though, with hydrocarbons. Okay? Only C and H, and if you can tell something is a hydrocarbon just from its formula, if it is C10H22 or something like that, that's a hydrocarbon just because it contains only C and H. That's it. Okay? So we are going to go through the 4 types of hydrocarbons, okay? And we're going to classify and draw and name them sort of as we go. So alkanes have only CC single bonds. Alkenes have at least 1 CC double bond. Alkynes have at least 1 CC triple bond. Okay? Altogether, alkanes, alkenes, alkynes are considered aliphatic. And that's an old historical term. We'll talk about that in a little while, I think. And then there are aromatic hydrocarbons that contain a benzene ring, a very specific ring formation that carbon and